So we have the pleasure of having Bernardo Lima from Minas Gerais giving our contributed talk in a workshop. And he'll be talking about embedding binary sequences into percolation, Z3.
Okay. Thank you, Roberto. First of all, I'd like to thank the opportunity to speak here. I use the slides on the end of the talk. I use the blackboard. I suppose that not all the audience is familiar with percolation. Then I will start with a very pedagogical introduction to percolation, at least something like 10 minutes. For people that works in percolation or it's familiar with percolation, I ask some patience. The simple model of percolation, I have some graph, a set of vertices, and a set of bonds, and a parameter, a real number in the interval 0, 1. During all the talk, we can suppose that our graph is ZD. Then the bond percolation model, each bond is open with probability P and closed with probability 1 minus P. And each bond is open or closed independent of each other. We can think like each bond is a kind of pipe, and this pipe allows or not to the flow of some liquid, water for example. This is the bond percolation model. But here, we will consider some variation of this model, is the site percolation model. In the site percolation, each bond is open. All bond is open. But we can think something like this. In each vertex, we have a kind of a tap, and this tap can be open or closed. Is it clear? This is the site percolation model. In each site could be open or closed. Is open with probability P and closed with probability 1 minus P. Then the probability space that describes this model is omega is 0, 1 to the power of the vertex set. We can think 0 as closed and 1 as open. F is the sigma algebra generated by cylinder sets, and PP is the product of Bernoulli measures with parameter P. Okay? Then, fixed some vertex V, we define the cluster of V is the set of the vertex U such that there exists some path gamma starting from V, V0, V1, V2, so on, and ending in U, such that Vi plus 1 is a bond of the graph, and the configuration on the vertex vi is 1. Is it clear, this definition? That is, if I put water under pressure on the vertex v, the cluster of v is the set of wet vertices. Okay? Now, I can define the probability function, the percolation function. Theta is a function in the interval 0, 1 to 0, 1, where theta p is the probability, this p is this p, of the set of configurations such that the cluster of the origin is infinite. Okay? And I define the critical point PC. This PC in general depends of the graph, is the supremum of the set of the P such that theta P is 0. Now I can state the first theorem in percolation by Broadbent and Hammersley. '57. If I consider the graph ZD for any D at least 2, there exists PC of D in the intervals 0, 1, such that this function theta p is 0 for p less than pc and is strictly positive for p bigger than pc. This is the subcritical phase. And this is supercritical phase. Probably you are thinking about, well, this is not only the definition of supremum. No, the main part of this theorem is the critical point is in the open interval. PC is not 0 nor 1. For example, if I consider D equals to 1, I am in Z. It's easy to see that the origin belongs to an infinite cluster if and only if all vertices at right to the origin or left to the origin are open. And this is true. That is, theta p is strictly positive if and only if p is 1. If I draw the graph of this function theta p, is something like this. Is it clear? That is, this case does not fit in this theory. This is the reason D should be at least 2. Okay? My second remark, observe that this theorem does not tell anything about what happens when P is equal to PC in the critical phase. What about theta of PC? We know that for D equals to 2, theta to PC is 0. This is Dewey, Harris, and Casting. 1980. Indeed, it's known that suppose that we have PC here. Of course, the function theta p is continuous below PC, and we know that this function is right continuous above PC. Then it's not difficult to see that to prove that theta of PC is 0 if and only if the function theta p is continuous. So if theta PC is 0, the graph should be like this. But in principle, could be theta of PC could be not 0. For example, could be like this. Okay? Was proved by Harris and Casting that for D equals to 2, this is 0. Some years later, was proved by Takashi Hara and Gordon Slade in 91 that for high dimension, theta of PC is also 0. And in a short note in 94, 19 is enough for this high dimension. That is, we know that this function is continuous for D equals to 2 and at least 19. And what's the behavior of theta PC for D between 3 and 18? Nobody knows. This is probably the most important open question in percolation. Open question. And my last remark, if I consider some graph translation invariant, we can see that this probability does not depend of the vertex of the, I can suppose, any vertex V, the distribution of the size of the cluster of the vertex V does not depend of the vertex V. Then for this class of the graphs, for example, ZD, if I consider the cluster of the V is infinite, union in V, this event is translation invariant, then by ergodicity, this probability should be 0 or 1. Or if you prefer, this event is a tail event, then by Kolmogorov 0-1 law, this probability should be 0 or 1. And this probability 1, we say that there's percolation. Okay? Is it clear for everybody, this introduction? Okay. Now, I finished. Yes. Now, I will define some variation of this percolation model, called percolation of words. This model was introduced by Beniamini and Casting. In 96, and the model is the following. A word, for me, is a binary sequence. It's a semi-infinite binary sequence, a sequence of zeros and ones. Okay? This is a word. I use the capital Xi to denote the set of the words. Then, this is the main definition. Given a vertex V, a configuration omega, and a word Xi, we say that the word Xi is seen from the vertex V on the configuration. Omega if there exists some path gamma starting from V, but now my path is semi-infinite, such that Vi plus 1 is a bond in my graph, and the configuration at the vertex vi coincides, it's equal to the ith digit of the word for any I. Now I'm defining what is the word Xi is seen from V on the configuration omega. That is let's suppose that here is V. Then I have some path. For example. And is given the word. Such that here I have X1, X2, X3, X4, X5, X6, and so on. Is it clear, this definition? Observe that in this definition, the configuration on the vertex V does not matter. Okay? And to short the notation, I would denote by S V omega is the set of the words such that Xi is seen from V on the configuration omega. That is the set of all words such that is seen from V in this configuration. And S infinite omega is the union of S V omega for all V. That is, this is the set of the words such that these words are seen from anywhere. Okay? Sure, sure. Thank you. And this path should be self-avoiding. Vi is different from Vj for any I different of j. Thank you. Okay? Now I can state the main theorem of this paper of Benjamin and Kasten. Well, before I state the theorem, observe that this model of percolation of the words in some sense generalizes the standard percolation. The standard percolation is when the word 11111 is seen. Is it clear? Indeed, there's another ancestral model of percolation of the words introduced by John Veerman. It's called by A-B percolation. We have a graph, and we have two kinds of particles, A and B. And I associate in each vertex one particle, A or B. Okay? And each bond is open if and only if one end is A and the other end is B. Then I have percolation on this model is equivalent to percolation of the word 1010101010. Okay. So, in this paper, they prove the following. Theorem, Benjamini and Kasten. site percolation. And ZD with parameter P equals to 1/2. It holds that A, the probability of the set of configurations such that S infinite is equal to the set of all words. This probability is 1 for any D at least 10. Part B, the same model, the probability of the set of configurations such that there exists some vertex V such that SV omega is equal to the set of all words. This probability is 1 for all D bigger than 40. That is, in high dimensions, we can see all words. If this high enough is at least 10, we can see all words starting anywhere. If D is higher, 40, we can see there exists some vertex such that I can see all words starting from this vertex. Is it clear, this theorem? Then, in this paper, there's a list of 3 open questions. And only one of these questions is still open today. Is the following. Part A. Is true for D. Not for D large enough, but for D equals to 3. In some minutes, should be clear that this is false for 2. Then the lowest dimension that this could be true is 3. Okay? Well, we don't have an answer for this question, but in this direction, we have some partial result. Then, all that I will speak from now on is a joint work with Marcelo Hilário, my colleague of UFMG, Pierre Nolan from ETH in Zurich, and Vladas Sidoravicius. From Then let me start with some simple definitions. Fixed some word xi. I will define the set I is the set of natural numbers such that xi is different of xi I plus 1. Now, I will define this sequence ij of xi at the following manner. I0 is 0. I1 is the minimum of the set. I2 is the minimum of the set. Capital I minus I1, and so on. Ij is the minimum of the set. Xi minus I1, Ij minus 1. And finally, I would find the sequence Lj, where Lj of xi is Ij minus Ij minus 1. Let's do some example. Suppose that my word is 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, and so on. Then, what is the set capital I? Capital I is the set of the index where my word changes from 0 to 1 or vice versa. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay? I0 is 0, I1 is 3, I2 is 5, and so on. And this sequence, Lj, L1 is 3, L2 is 2, L3 is 2 again, L4 is 4. That is, this sequence L is the length of the blocks of consecutive digits. Is it clear? Observe that if this set is finite, for example, this is only well defined if this set is an infinite set. If the cardinality of this set is finite, that is, my sequence xi ends with 0, 0, 0, 0, 0, 0, and so on, or 1, 1, 1, 1, 1, 1, 1, we say that the word is ultimately monochromatic. And I use this notation for the set of the words of ultimately monochromatic. Okay? Definition. Given a positive integer m, we say that the word is m stretched if Lj of psi is at least m for any j. That is, my word is m stretched if each block of consecutive digits we have at least m digits. Is it clear, this definition? And I will call by capital Psi m is the set of the words such that Xi is m stretched. Now I can state there's anything else to say. Before the theorem, one important remark. For standard ordinary site percolation was proved by Campanino and Russo in 83 that the percolation threshold for Z3 is less than 1/2. Then PC for ZD is less than 1/2 for any D at least 3. Okay? Why this is important? This is important for us because suppose that here is the interval 0, 1. This is 1/2. This is PC. So, this interval is the supercritical phase for percolation of ones. Okay? And this region, oh, sorry. Here is 1 minus PC. And this region is the supercritical phase for percolation of zeros. If PC is the percolation threshold for percolation of ones, 1 minus PC is the percolation threshold for percolation of zeros. Then, this interval between PC and 1 minus PC we have percolation of both monochromatic words, zeros and ones. This is very important for us. Is it clear? Then, our theorem is the following. Hilário, myself, Nolan, and Sidoravicius. For ZD, for D bigger than 3, and P between PC of D and 1 minus PC of D in this interval. There exists some large integer n. This n depends on p, such that the probability of the set of configurations such that the set of the words that are seen contains the set of m-stretched words with probability 1. That is, we are not able to prove the open question. We can see all words, but we have a partial result. We can see all m-stretched words for some large m. Is it clear, the statement of the result? Now, I would like to some remarks about this theorem. I forget something. Well, the first remark is almost a triviality. In this interval, we have percolation of ones and percolation of zeros. So it's very easy to see that we have percolation of all ultimately monochromatic words. That, indeed, we can prove that in this situation, the set of the words contains not only the m-stretched words, but contains also the set of ultimately monochromatic words. My second remark is that there is says that for high dimension, for large D, we have a much more simple proof of this theorem, and more than this, for large D and P equals equals to 1/2. We can take m equals to 2. And this proof is very simple. First of all, what is large enough? Large enough for me is large enough if PC of ZD minus 1 is less than 1/4. It's a simple exercise of percolation to prove that PC of ZD goes to 0 when the dimension goes to infinite. So, for some D large enough, the percolation threshold becomes less than 1/4. Then, suppose that D is large enough such that this is true. Some simulations suggest that PC of Z4 it's around this. That is 5 is large enough for us. The proof in this case of large D is the following. Then my space is ZD, but let's concentrate in this subset. It's ZD minus 1 times 0, 1. This is a D-dimensional slab of ZD. Okay? Given some vertex with coordinates V1, VD minus 1 on ZD, we say that this vertex is good if for the vertices V prime is V1, VD minus 1, 0, and V double prime is V1, VD minus 1, 1. We have that the configuration on V prime is 0, and the configuration on V double prime is 1. Okay? Then observe that when P is 1/2, the probability of some vertex V is good, is 1/4. I'm looking for some 0 here and a 1 here, and the model is independent. 1/2 times 1/2, 1/4. And 1/4 is bigger than PC of D minus 1. So we have percolation of good vertices on ZD minus 1. Okay? Well, suppose that this is ZD minus 1 times 0. Here, the other 4, we have ZD minus 1 times 1. if I have percolation of good vertices on ZD minus 1, this is implied that I have some infinite path of zeros here, and just below an infinite path of ones here. That is, if I look in this direction, I have an infinite path of zeros and an infinite path of ones. Then, given any word at least two stretched, for example, 0, 0, 1, 1, 1, 0, 0, 0 is only 2. I take 2 zeros, then 4 ones, now 3 zeros. Is it clear? I have only problem if I have some single 1 or some single 0. Okay. My last remark. I would like to convince the audience that why, in some sense, our theorem is not trivial. In this paper of percolation of words by Benjamin and Kasten, they consider also the situation where the digits of the word are IID random variables with distribution of Bernoulli with some parameter alpha. That the set of the words now is a probability space. The sigma algebra is the sigma algebra generated by cylinder sets. And I have the measure mu alpha, where mu alpha is a product of Bernoulli measures with parameter alpha. Okay? And in the Benjamin and Kasten's paper, they prove the following. Well, this first part is not it's almost standard. The probability of the set of configurations such that the word xi is seen let's call this whole xi. This probability is 0 or 1 for any word. Okay? The second part is more interesting. It's a very smart application of Kolmogorov's 0-1 law. The measure of the set of the words such that, and sorry, when this is 1, we say that the word xi percolates. Okay? The measure of the set of the words such that xi percolates, this probability is also 0 or 1. By Fubini theorem, this is equal to the probability of the set of configurations. configurations such that the measure of the set of the words that are seen is 1. Then, when this is 1, we say that almost all words percolate. Okay? Almost all, because we cannot say that this is the set of all words, but I can say only that the measure of the set of the words that percolate is 1. Now, by some very smart construction by John Veerman, we can prove that for any p and for any word, we have the following. The probability of C is seen from the origin is at least the minimum of the probability of the word 11111 is seen from the origin, and the probability of the word 000 is seen from the origin. Indeed, this argument by John Veerman, he proved only for p equals to 1/2, and in the alternating word 101010, this word, the probability of percolation of this word is at least the probability of percolation of the monochromatic word. This generalization I did in some paper some years ago, but it's a very simple argument. The difficult part is the original result of Veerman. Okay, the generalization for any p and any word is almost trivial. Okay, if this is true, observe that for p, if I have, this is very general for any graph. If I have some graph where pc is less than 1/2, if I consider this interval between pc and 1 minus pc, I have percolation of both monochromatic words. Then this is strictly positive, this is strictly positive, so the minimum is strictly positive, then this is strictly positive, then this should be 1. Okay? That is, for p in this interval, all words, given any word, this word percolates. But this does not imply that the set of the words that are seen is the whole set of the words, because the set of the words, it's a non-countable set. An intersection of events of probability 1, if this intersection is a non-countable intersection, I cannot say that the probability is also 1. Okay? Of course, this implies that the probability, if p in this interval, the probability of the set of configurations such that S infinite contains some set x, this probability is 1 for any x countable. Okay? So in some sense, our theorem is not trivial, because this set, the set of m-structured words, It's a not countable set. Okay? Now, how many time I have? How much time I have? Yes, but I would like to give a very, very fast and short sketch of the proof. Is it clear, the statement of the result? And the remarks? Okay. To prove this theorem, it's enough to consider the more difficult situation is when d equals to 3. Then I give this outline of the proof for d equals to 3. And for me, Z3 star is the Z3 lattice shifted by this vector, 0, 1/2, 1/2. And during the proof, I will fix some p in this interval. Okay? Oops. Now I will define this structure, an outlet. What is an outlet? Suppose that the plane of the screen is the YZ plane. The x-axis is orthogonal to the plane of the screen. Okay? And consider these 8 vertices. We have the origin. Tem luzinha aqui? Luzinha? Here is the origin. And this vertex, for example, is 0, 1/2, 1/2, 0, 1/2, 3/2, and so on. And we say that this structure is an outlet if and only if these 4 vertices in black, the configuration is 1, and this other 4 vertices, the configuration is 0. Okay? Only this. 4 vertices 0 and 4 1s. This is an outlet. Parou. Onde que eu desliguei? Now I will define what is a L outlet. L is some large integer, and I have some, for example, this rectangle RL1 is this rectangle, and we have these 4 rectangles, and I have a L outlet if I have an outlet in the centrum, and starting from this vertex, I have some path of 1s connecting this vertex to the right side of this rectangle. Okay? And I have analogous crossings, a crossing of 1s from this vertex to the left side of this rectangle, and the same below, but path of 0s. Okay? This is an L outlet. Then, is it possible to prove that fixed P, there exists some number, some positive number delta and some L1 large enough, such that the probability of there's a L outlet at the origin is at least delta 1. Okay? Now I will perform a kind of block argument, some static renormalization. I will consider this set of vertices. L is fixed, and I will consider the vertex with this form. For I, the vertex Vij has coordinates 4IL and 12IL, and the third coordinate is 0. Here in the plane of the screen is the xy plane, and in each vertex I put some box like this. It's very important to observe that in the x direction, this box, the length is 4L. Observe that in the definition of outlet, in the x direction, it's only 2L. This is very important for me. Then, putting these spectral boxes in each vertex like this, I have this structure, and it's easy to see that this graph where I think each box as a vertex. Then this graph is isomorphic to this graph. Okay? Then I will define what is each block BL is good. The box BL is good if there exists some K in this interval such that in the vertex K0L I have some L outlet. So this is the reason such that it's important that this length is the double of the length of the L outlet, because I have some freedom to looking for my outlet here. Okay? My outlet, in some sense, it's around in the centrum of this box, but not exactly in the centrum. So, is it possible to find some outlet with high probability? And let me speed up. And the second condition is that this event occurs. This event is the following. It's better I explain in the figure. I have in the supercritical phase, and it's a standard result that at the supercritical phase, the infinite cluster is unique. Then, the second condition says that if I have some large path of 1 here in this box, and some large path of 1s here in this square, these crossings must be connected. Okay? This is due by the uniqueness of the infinite cluster. This small piece is large enough for this. Okay? And we have the same for the crossings of 0 in the first floor. This is the definition of a good block. Then we can prove that the probability of some block is good. This probability goes to 1 when L goes to infinite. Then I have some infinite path of good blocks. It's important to observe here that the status of good for each block is not an independent percolation process. Because, for example, this block, this shadow block, is good, and this other block here is good. They have some intersection. They share the same part of the space. So, both are good, are not an independent thing. But it's a two-dependent percolation. So we can use this standard result of Liggett, Schoenman, and Stacy for finite dependent percolation process. And if this probability is large enough, then we have percolation of good blocks. Then, is it possible to prove that exactly this? there exists some L2 large enough such that almost surely there exists some infinite path of good blocks in my renormalized lattice. But if I have an infinite path of good blocks, what I have in the original lattice? I have this structure. My outlets, an infinite path with infinite outlets, and these outlets are connected by 1 paths here and 0 paths here. And in this construction, it's also important that the distance between 2 consecutive outlets has an upper bound. This is trivial because in the worst case, the volume of 2 blocks is this upper bound. And finally, we can prove this result. Let's call small l this upper bound. If m0 is L squared, then almost surely all m0 stretched sequence can be embedded in this structure. This is not so trivial to prove this lemma, but essentially it's a combinatorial exercise. Then I have this structure with probability 1, and is it possible to see all sequence in this structure? Okay, then this proves this theorem.